the properties of these conormal points. First property among them is sum of the eccentric angles of conormal points is an odd multiple of. Now, how can you find the sum of these eccentric angles? First of all, let us take alpha, beta, gamma and delta. These are the four eccentric angles of the conormal points on the ellipse. On the ellipse, x square by a square plus y square by b square is equal to 1. Employs from previous concept that here this is the equation we had. So hence we had that equation as bk t power 4 is 2 into ah plus a square minus b square into t cube plus 2 into ah minus a square minus b square into t minus bk is equal to 0. This is a biquadratic equation which represent four normals. Let t has four values. It is tan of alpha by 2, tan of beta by 2 and tan of gamma by 2 and tan of delta by 2. These are the four values of t. So therefore from the compound angle what we had is tan of alpha by 2 plus beta by 2 plus gamma by 2 plus delta by 2 is equal to. This formula can be expressed in terms of S1, that is sum of the factors taken. First one, that is alpha by tan alpha by 2 plus tan by 2. Next S3 by 1 minus S2 plus S4 from the trigonometric transformations. Therefore S1 is sum of the roots, that is equals to, if you take S1 is this one divided by this one, and S3 is sum of the product of the roots taken 3 at a time. S4 is simply product of the roots. If you can substitute and simplify, then you will get 2 into AH plus A square minus B square by BK plus 2 into AH minus A square minus B square by BK is total divided by 1 0 minus 1. Here what is happening is plus 1 minus 1 cancel and denominator becomes 0. Therefore this is undefined infinity. That implies here tan of this one is undefined, then alpha by 2 plus beta by 2 plus gamma by 2 plus delta by 2 can become any odd multiple of 90 where all n belongs to integer. Implies that is alpha plus beta plus gamma plus delta is equals to 2 gets cancelled, this become 2n plus 1 into pi. That is odd multiple of 180. Therefore we conclude is sum of the eccentric angles of conormal points is always odd multiple of 180, that is pi. Therefore what we have proved the property is sum of all the eccentric angles of conormal points an ellipse is always odd multiple of 180. The sum of eccentric angles of conormal points is the odd multiple of 180. Let us understand the concept by means of the animation related here. This is x-axis, the y-axis and horizon. This is the ellipse and this is the auxiliary circle, and A is a point on it whose eccentric angle is theta 1, and B is a point on ellipse eccentric angle theta 2, C is a point on ellipse eccentric angle theta 3, and D is a point on it eccentric angle is theta 4. Here you observe that this we have taken as alpha, this is beta, and this is gamma, and this is delta. And we have proved that the sum of the eccentric angles of 4 points which are situated on the ellipse is 2n plus 1 pi, where n is a positive integer. So that is nothing but sum of all eccentric angles of 4 points which are on the ellipse x square by a square plus y square by b square equal to 1 is proved to be odd multiple of 180, which is odd multiple of 180. So this is an animation which helps us in understanding this concept, even odd multiple of 180 which is odd multiple of 180. So this is an animation which helps us in understanding this concept even better. Next, let us go to the property number 2. If alpha, beta, gamma, delta are the eccentric angles of conormal points, then sigma, first one is sigma of cos alpha plus beta is 0, and second one is sigma of sin alpha plus beta is 0. Let's have the proof of this one in this way. From Euler's theorem in trigonometry, we have e power I theta is equals to cos of theta plus I sin theta, and e power minus I theta is cos of theta minus I sin theta. From this we can write, if we take z as e to the power of I theta, then obviously z bar will become e to the power of minus I theta. So from this we can find it out. Z plus 1 by z by 2 is nothing but cos of theta, and z minus 1 by z by 2i is equals to sin of theta. So from this what we conclude is z square plus 1 by 2z is cos theta, and z square minus 1 by 2i into z is sin theta. So these are the assumptions that we have made. Now from this equation of normal is in the form of ax by cos of theta and by sin of theta is equals to a square minus b square, where here I can take h comma k as the point where all these point h comma k be the point where these normals are meeting. Then it become ah by z square plus 1 by 2z for cos theta, and bk by z square minus 1 by 2i into z for sin theta, and a square minus b square is left. If I simplify, then I'll get a equation like a square minus b square into z power 4 minus 2 into ah minus ibk into z cube plus 2 into ah plus ibk into z minus a square minus b square is equals to 0. This is what is a biquadratic equation in terms of z. When it is biquadratic equation in terms of this, let this equation has z1, z2, z3 and z4 as roots. As it is in terms of z and it is biquadratic, let it has the roots. When it has the roots, then from theory of equation we have product of the root z1, z2, z3, z4 becomes is equals to minus 1, which can be written as e power I alpha into e power I beta into e power I gamma into e power I delta, which can be written as e to the power of I is taken common, alpha plus beta plus gamma plus delta from the theory of indices. So this minus 1 can be expressed as minus 1 plus 0 into I. So e power I into alpha plus beta plus gamma plus delta can be taken as such. Now if I write this e to the power of expansion in terms of cos and sine using the Euler's theorem, this will become cos of alpha plus beta plus gamma plus delta plus I into sine of alpha plus beta plus gamma plus delta, which is equal to minus 1 plus 0i. So on comparing, obviously here I'll get cos of alpha plus beta plus gamma plus delta as minus 1, and the sine of alpha plus beta plus gamma plus delta is equals to 0. So this is possible from this equation. Let us give the equation as number 1. Further, again from equation 2 using theory of equations, we had again from the equation 2 using theory of equation, what we had is sigma of z1 and z2 is 0. That implies z1 z2 plus z1 z3 plus z1 z4 plus z2 z3 plus z3 z4 z2 z3 plus z2 z4 plus last one z3 z4. This is actually the cyclic terms, sum of the cyclic terms. Now if I can write this in Euler's theorem, e power I alpha into e power I beta, e power I alpha, that is e power I gamma plus e to the power of I alpha into e to the power of I delta, e to the power of I beta into e to the power of I gamma, and e to the power of I beta into e to the power of I delta, e to the power of I gamma into e to the power of I delta is equals to 0. Implies it becomes e to the power of I into alpha plus beta plus e to the power of I into alpha plus gamma, e to the power of I into alpha plus delta plus e to the power of I into beta plus gamma plus e to the power of I into beta plus delta plus e to the power of I into gamma plus delta is equals to 0. Obviously when summation is equal to 0, each term must be equal to 0, therefore this must be 0 plus 0i. Hence this becomes cos of alpha plus beta plus cos of alpha plus gamma plus cos of alpha plus delta plus cos of beta plus gamma plus cos of beta plus delta plus cos of gamma plus delta plus I into sine of all these things once again from alpha plus beta 2. From alpha plus beta 2, the last term what we had is sine of beta plus delta and sine of gamma plus delta. This is equal to 0 plus 0. Finally, what we can conclude is sigma of cos of alpha plus beta is 0 and sigma of sine of alpha plus beta is 0, as this summation becomes 0 and this summation becomes 0. This is property number 2. Next, let us go to the property number 3. To understand the property number 3, let us go to the animation related to this property. This is x-axis and y-axis origin and ellipse. These are point A with alpha eccentric angle, B with beta and C with gamma. All these are meeting at a point. So the question here is, if alpha, beta, gamma are the three eccentric angles of 3 points on the ellipse x square by a square plus y square by b square equal to 1, and the normals at these points are concurrent. These are the normals are concurrent at this. Then is asking to show that sine of alpha plus beta, sine of beta plus gamma plus sine of gamma plus alpha is 0. Okay, we'll prove this using the previous property, that we had this alpha, beta, gamma or the eccentric angles of 3 points. From the figure we had A, B, C are the 3 points and their normals are concurrent. From the figure, the 3 normals at A, comma, B, comma, C are concurrent. All these 3 points are meeting at a point. The normals of these 3 points. So therefore, from previous property, that is property number 2. What is the property number 2? We have, that is sine of alpha plus beta plus sine of alpha plus gamma plus sine of alpha plus delta plus sine of beta plus gamma plus sine of beta plus delta, and last one is sine of gamma plus delta. This is equals to 0. But alpha plus beta plus gamma plus delta is already odd multiple of 180. So therefore here what I required is only the terms till alpha, beta, gamma. Wherever I will find delta, that I would like to replace in this way. Employs. Here it is okay, alpha plus beta and alpha plus gamma is fine. Alpha plus delta I would like to replace this one. That is alpha plus delta can be written as here odd multiple, that is 2n plus 1 pi minus of the rest of the thing alpha and delta cancel, that is beta plus gamma. Similarly here beta plus gamma is required and beta plus delta I would like to replace it as beta plus delta is equals to 2n plus 1 pi minus of left with alpha plus gamma, and gamma plus delta I would like to replace as gamma plus delta is equals to 2n plus 1 pi minus of alpha plus beta. So here if I apply sine to all these things, obviously here this sine of alpha plus delta will become as sine of beta plus gamma, and the sine of beta plus delta will become sine of alpha plus gamma, and the sine of gamma plus delta will become as sine of alpha plus beta. When I replace this one by sine of beta plus gamma and this one by sine of alpha plus gamma and this one by sine of alpha plus beta, therefore I will find 2 sine alpha plus betas, 2 sine alpha gamma and 2 sine beta gamma. Therefore I will get this is 2 into sine of alpha plus beta plus sine of beta plus gamma plus sine of gamma plus alpha, which is equals to 0. This 2 gets cancelled. Finally what is left is we had sine of alpha plus beta plus sine of beta plus gamma plus sine of gamma plus alpha is equals to 0. This is the property what we have proved just. This property number 3. Next let us go to the property number 4. The normal at x1, y1, x2, y2 and x3, y3 and x4, y4 on the ellipse x square by a square plus y square by b square equal to 1 are concurrent, then x1 plus x2 plus x3 plus x4 into 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4 is equal to 4. For better understanding, let us go to the animation related to this problem in this way. X-axis and y-axis, and that is ellipse, and x1 y1 is a point, x2 y2 is a point, x3 y3 is a point, and x4 y4. All these points are having their normals intersecting at this point M. So you need to prove this condition which is mentioned in the theorem. Let us proceed in this way. Now let us take P of x0 y0. This is B, any point on the ellipse. any point on the ellipse x square by a square plus y square by b square equal to 1. When this be any point on the ellipse, obviously it will satisfy the ellipse. So y naught square value will get it as b square by a square into a square minus x naught square. This is the value of y square which is used in further due course. And let us take this h comma k will be the point of intersection, and m is equal to h comma k will be the point of concurrent. It is point of concurrent of all four normals representing at P. So at P you are taking P may be this point or this point or this point or this point, anything. Therefore, equation to the normal at the sample point P of x naught y naught become y minus y naught is equals to slope is obviously a square y1 a square y naught and b square x naught into x minus x naught, and this is a normal equation which is passing through. This is passing through h comma k, obvious, so concurrent. Therefore, this can become k minus y naught, which is equals to a square y naught by b square x naught into h minus x naught. If I cross multiply this and squaring on both sides, so here cross multiply and square on both sides, then I'll get an equation in this form. If I cross multiply and square on both sides, then I'll get an equation in this form: y naught square into a square into h minus x naught plus b square x naught whole square is equals to k square into b to the power of 4 into x naught square. In this you put y naught value, what we had y naught square value as b square by a square into a square minus x naught square. If I put this value here in this, put this value, and on simplifying we will get this as b square by a square into a square minus x naught square into a square into h minus x naught plus b square x naught square is equals to a square b power 4 into x naught square. Now the equation becomes a square minus b square whole square times of x naught power 4 minus 2 into a square h into a square minus b square in times of x naught cube plus a square b square k square minus a square times of b square minus a square whole square, plus this is added with a power 4 h square times of x naught square, and here 2 into a power 4 into h times of a square minus b square times of x naught with the constant a power 6 h square is equals to 0. This is the simplified equation what we had earlier, that is equation 2. Now this is biquadratic in x naught. Now as it is biquadratic in x naught, which has the roots as x1, x2, x3 and x4, because we have taken x naught, y naught be any point among them. So therefore from theory of equations what we had is x1 plus x2 plus x3 plus x4 is s1, that is this becomes minus into minus plus, this is 2a square h into a square minus b square divided by the a square minus b square whole square. So which is equals to 2 into h into a square by a square minus b square. Let it be number 1. We will take this number 2, already number 1 is taken. And also 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4. If you can simplify, it becomes product LCM is x1, x2, x3, x4, and here this become x2, x3, x4, this become x1, x3, x4, this become x1, x2, x4, and this become x1, x2, x3. So we can take sigma of simply x1, x2, x3, which is equals to s3, that is this is s1, s2, s3, that is minus into minus plus 2 into a power 4 h times of a square minus b square divided by the coefficient of the top term a square minus b square whole square divided by x1, x2, x3 is a product, that is a power 6 h square divided by this, that is a square minus b square whole square. Now if I simplify this, a square minus b square whole square gets away, and here a power 4 gets cancelled twice and h cancels once, leaves you here 2 into nothing left, that is a square minus b square by denominator is a square into h. Say this is number 3. So therefore here we have x1 plus x2 plus x3 plus x4 times of 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4 is equals to the product of these two, that is 2h a square by a square minus b square times of 2 into a square minus b square by a square h. So here 2 a square minus b square moves off and a square moves off, h moves off, leaving with 2 into 2 is 4. So therefore what we have concluded is if x1 y1 and x2 y2 are if x1 y1 x2 y2 x3 y3 and x4 y4 are the 4 points on the ellipse with eccentric angle, or the 4 points whose normals are concurrent, then x1 plus x2 plus x3 plus x4 times of 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4 is equals to 4. This is the last property what we have proved. Now observe that there is a note point related to this property, that if alpha, beta, gamma, delta are the eccentric angles of the normals drawn at P, then by replacing this x1, x2, x3, x4 by a cos alpha, a cos beta, a cos gamma, a cos delta respectively in the above result, we get this one. That is, here we have proved already this one, x1 plus x2 plus x3 plus x4 times of 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4 is 4. So in this is asking to place x1 as a cos alpha and x2 as a cos beta and x3 as a cos gamma and x4 as a cos delta. When you replace them, then that implies this becomes a is taken common, that is cos alpha plus cos beta plus cos gamma plus cos delta into times of 1 by cos is secant and 1 by cos is secant, 1 by cos is secant and 1 by cos is secant. This is equals to 4 and here bracket, and here what we had is 1 by this by a is equals to 4. This a and this a moves off, therefore you can write it as sigma of cos alpha and this is sigma of secant alpha is equals to 4. That is what you can prove also.